Okay, this is going to be our seventh and final video in our electric charge and electric field series. So in this video we're going to begin with, we're going to begin by looking at electric field lines. It's going to be a short sort of discussion on electric field lines, and then we're going to move on to electric dipoles. Okay, so electric field lines. Electric field lines are imaginary lines or curves that are drawn through a region of space that are everywhere tangent to our electric field at all points. Okay, and so we can kind of see. Maybe it would help if I had these pictures on screen as I talk about it. So these diagrams that we have down below here, these are figure 21.28 from the text. So we can see that electric field lines will always emerge from positive charges, and they'll terminate at negative charges. They also never intersect. Okay, and we can kind of see how they've drawn in nicely the electric field at different points, and we can see that these electric field lines are in fact everywhere tangent to our electric field, right? We can see it really clearly here in the case of this single positive charge. We can see everywhere that our electric field should be pointing away, and so the electric field lines point away everywhere. And as we add in more charges into the region that we're looking at, things get more complicated, right? So in 2 we can see the lines emerging from the positive charge and ending in the negative charge. And with 2 positive charges we can see that things get a little more complicated, and the electric field lines have nowhere to terminate here, so they kind of form these interesting shapes, right? And so there's a few important things to remember here. So electric field lines are not trajectories. Okay, so electric field lines aren't showing us how a particle would travel, a charged particle trapped in this field would travel, right? It's showing us where the electric field points at all the points. So the acceleration of a charged particle in this field would actually end up being tangent to these electric field lines at every point. So not following the electric field lines, but you can get the acceleration vector at any point by looking at these lines, right? Another interesting note is that the spacing of the electric field lines kind of gives us a qualitative feel for the strength of the electric field at that point. So if you had a very strong charge, you would draw more electric field lines. Maybe I'll just do a little quick example here. I probably won't leave this here, but just for you guys to see. So if you had a very small positive charge, your electric field lines maybe would look something like this, right? This is for some small positive Q. But if you had a very large, like a very large positive charge here, you would draw more field lines, right? This is to indicate that you had a much stronger charge at this point. Okay. And that's just kind of an interesting way to sort of visualize what's going on with the electric field there. Oh no, did I lose? Oh, I did lose it. Let me pause and reopen that one sec. Okay. Okay, so like I was saying, basically, I mean, there's not a lot more to say about the electric field. You can kind of look at this. It gives you a nice way to visualize what the electric field is doing. We can't really do many calculations with it, but it's a good way to get a sort of feel for what's happening. Okay. And so I'm going to move on here. We're going to move on to well, this previous section that we just did, this corresponds to 21.6 in the textbook. We're going to move on to 21.7, which is the last section in chapter 21 that we're going to be looking at. And this section deals with electric dipoles. So an electric dipole is a pair of charges, each of which has equal magnitude, but an opposite sign, and they're connected by some distance d. Okay, and we see a nice diagram of this here from figure 21.31 in the text. Okay, and so we have our dipole here. This is our dipole connected by some distance d, and it's sitting in an electric field. We can see these large purple lines. These correspond to an electric field pointing to the right here, to our positive I hat direction if we have a coordinate system imposed on here, right? Okay. And so we want to take a look at sort of what happens to this dipole in this electric field. Okay, so the first question would be, well, what is the net force on this dipole in the electric field, right? And the answer to that would be there is no net force on the dipole because we have our positive charge experiencing a force to the right and our negative charge experiencing a force to the left, they cancel out and there is no net charge. And again, this is assuming that we're in a uniform electric field, right? If the electric field was noticeably stronger on the right-hand side of our dipole than it was on the left or something, then there would be a net charge, right? But in general, these dipoles are very, very small, and so in a regular electric field, which is pretty homogeneous over those scales, which is pretty sort of uniform over those scales, we wouldn't have any difference, right? And so even though there is no net force, the two forces don't act along the same line here, right? Like if we take a look at our two forces here, we see the force from the negative charge in our dipole acting in this direction, and our positive charge in our dipole has a force acting in this direction. So these two forces aren't acting on the same line. So even though there's no net force, there is going to be a net torque. Okay, our torques don't sum to zero in this case. So we're gonna let the angle between the electric field and our dipole axis, this line that connects our two different charges, be phi here. And if that's the case, then the magnitude of our torques resulting from our positive charge and from our negative charge are each this expression that we see here. And so the net torque is this equation that we see here, okay? And to make this kind of easier to work with, we also give the product of Q and D a special name, and we call that the electric dipole moment. So what is Q and what is D? Let's remind ourselves. D is the distance between our positive and our negative charge, okay? And Q is just the charge on the positive, well, the magnitude of the charge on the positive or negative charge, right? They have to have the same magnitude, and so they're both Q. One is positive and one's negative, but the magnitude is Q, and our distance is D, and we give P, this symbol P, what we call our electric dipole moment, this definition. It's the product of Q and D, okay? In SI units, P is going to be measured in Coulomb meters. And we also define the quantity P vector as this magnitude that we just talked about, pointing along the dipole axis from the negative charge to the positive charge. So we kind of have it drawn on here. So we have this would be our P vector. It points in the direction that the line drawn between the negative and positive charge would run, right? And it points from the negative charge to the positive charge. So I'll often draw these kind of like D, like I would draw this like on here like this, and I would call this P usually, right? And it would have a magnitude. The magnitude of my vector here would be D times Q, right? But I'll leave it the way they drew it here. And so having defined this P both as a scalar and a vector, we have these expressions for our torque. Okay, so this is our scalar expression, which is P E sine phi, and for the vector expression we have P cross E here. And so this is the first time in this course that we're seeing a cross product. But you guys saw cross products in your 111 class, often referred to as a vector product. So if you don't remember sort of how those work, maybe take a second here, go back and look at your notes. We're going to be using cross products a fair bit in this course, and you need to be fairly confident in being able to evaluate and use them. Okay. And so let's remember that we can use the right-hand rule to determine the direction of tau here from this idea of a cross product, right? So if we think about it, and do I have a nice example here? Yeah, I guess we kind of do. If we're looking at P cross E, we can see the direction that tau is going to point in. So if we use our right hand and we put our index finger in the direction of P, and then our middle finger in the direction of the electric field, our thumb will point in the direction of tau, and so in this case tau is into the page, right? And so let's keep on moving here. Where were we here? Right. So we can see here that that these equations that the, so what the torque is trying to do is the torque is always trying to turn P to point in the direction of E, right? So our torque will be greatest, and I wish I had this thing on screen all the time, but torque will be greatest when our P is 90 degrees to our electric field, right? So if P is pointing straight up and our electric field is to the right, or P is pointing straight down and our electric field is to the right, our torque will have the greatest magnitude at those points. Or it'll have the least magnitude, obviously, when our dipole is in one of the equilibrium states possible here, right? So if the dipole is lined up, if P is lined up with E, then we're going to have no net force, right? There's going to be no force acting on, well, there's going to be no net torque. I should say we have no net force anywhere, but there's going to be no net torque acting on the dipole. And if we have it lined up so that P and E are pointing in the same direction, we can kind of already see that this is going to be a stable equilibrium, right? If you tap the dipole slightly and it's lined up in this way, it'll just quickly reset itself back to where P and E are pointing in the same direction. There's also an unstable equilibrium if we had P pointing in the negative I hat direction, like P pointing off to the left here, and our electric field pointing to the right. That would be an unstable equilibrium. If it was perfectly set up that way, yes, the dipole would sit there and not move. But if we slightly perturbed this thing, if we knocked the dipole slightly, then it would spin all the way around until P was pointing in the direction of E, right? So those are our two sort of equilibrium positions for our dipole in this electric field. Okay, so one more little topic, and then we'll do a couple of examples with these. But we want to talk about the potential energy of an electric dipole in an electric field. So when a dipole changes direction in an electric field, the electric field does work on it, and it changes the potential energy of our system. Okay, so the infinitesimal amount of work, which we're going to label dW here, done by the torque during this infinitesimal displacement that we want to look at, and this is not correct. That should be a phi. So the infinitesimal displacement d phi is given by this expression that we see here. And there's a little bit of minus sign ambiguity here, but the reason we have a minus sign here is because of the change in phi for the diagram that we have above would be in the negative direction. Okay. And so then, over some finite displacement, so let's say we had our dipole sitting in an electric field for some finite displacement from phi 1 to phi 2, the total work done on the dipole by the electric field is given by the expression that we see here, right? So we have this definite integral, and we would integrate this over phi, right? So if we did that, we would find the result that we see here. And then if we remember from our work in 111, we know that work can be thought of as the negative of the change in potential energy. So this kind of leads us to a way to define the potential energy for the system, and we can define the potential energy for the system as we see here, right? This is it in its scalar form, or in its vector form. We have it here, right? So I didn't really bother to box these equations as I was going, but maybe I'll do that now. So you're definitely going to want to remember that this is true. I mean, all of these equations are going to be pretty important. So this is an important equation. And again, I'm going to put all of these on an equation sheet as we go on. Both of these forms are going to be important. So you want to remember both of those. It's probably not box worthy for me to put boxes around equations 5 and 6, but for sure you're going to want to remember equation 7. I mean, 5 and 6, like the way you get to it is important to remember. You want to remember how to do that, but it's not an equation that I would box. But as I said, 7 and 8 here are both going to be important, so those both deserve boxes. Okay, let's move on and do a couple of examples. I'm going to quickly pause and save this so I don't lose it again. I'll be right back. Okay, I'm back, so let's continue with our examples here. Okay, so our first example, we're going to be looking at the force and the torque on an electric dipole. This electric dipole, again, is sitting in some electric field, uniform electric field here. So when I say uniform, I mean uniform definitely on the scale of the dipole that we're looking at, okay? And so we're given some information here. We have our diagram. We are told that the magnitude of the electric field is 5 times 10 to the 5th newtons per coulomb. We're told that, well, we're given some other information. We're told that the charges on the dipole are the value that we see here, and that they're separated by this distance. And we're asked to find the net force exerted by the field on the dipole, the magnitude and the direction of the dipole moment, the magnitude and direction of the torque, and the potential energy of the system in the configuration that we see here. Okay, so let's get to work on this. I'll try to keep this diagram visible for as long as I can. So A was asking us for the net force on the dipole. Well, like we said before, there is going to be no net force on the dipole. Why is that? Well, that's because the magnitude of the force experienced by our negative charge. Well, okay, maybe I'll make it a vector. So the force experienced by our negative charge. Well, that's going to be, again, just some f, but this is going to point in the negative I hat direction. And the force experienced by our positive charge, that's again going to be some f, and it's not important that I actually calculate this because we're going to see that they cancel. This one's going to point in the I hat direction, and so if you add them up, they're a vector sum. If you add them up, you're going to end up finding that the magnitude of the resulting vector is just going to go to 0, right? So this is our net force, the magnitude of our net force. This is 0. So there is no net force acting on our dipole. Okay. In part B, we are asked to find, we want to find P, right? So we want to find the magnitude and direction of our electric dipole moment. That's our P. Okay, so we can very easily find the magnitude, and then there's a couple of ways. So the text does it one way. I'm also going to do it a sort of more vector-driven way also, so we'll take a look at 2 ways to do this. First of all, we want the magnitude. So the magnitude is just going to be QD. We can just multiply. So we're given Q and D up here, and we can just multiply those together here. So I'll just do that multiplication very quickly here. We end up with 1.6, and then the prefactor on our distance is this. And if we multiply the powers of 10 out front on our distance and our charge, we're going to end up with a 10 to the minus 28. And if we do that, well, this is going to be in coulomb meters. And if we do the whole calculation, we're going to find that our dipole moment here has a magnitude of 2 times 10 to the minus 29 coulomb meters. Okay, that's our P magnitude. So we can see that it points, well, that our dipole moment points from the negative to the positive charge, right? So we can see that our dipole moment, I'll draw it onto here, would point something like this, right? And so we can see that it really points sort of 145 degrees clockwise from E, right? So that's sort of one way to describe the direction, right? We could say points 145 degrees clockwise from E, right? But if we wanted to impose a coordinate system on this, let's say I called this I hat and I called this J hat, we could then describe this in terms of vectors, right? So let's say we wanted to describe this in terms of a unit vector pointing in the p hat direction, right? So let's take a quick little look here. We could yeah, maybe I'll redraw it here. So let's say we have our coordinate system set up like this. This is our x direction. This is our y direction. We can see that from this here, our p, or p hat is going to point in this direction, right? So let's say this was p. We would have we know that this angle in here is 145 degrees, so that means that this angle here must be 55 degrees, right? And this would be our px, and this vertical component here would be our py. So what would our, so in terms of p, in terms of whatever we want p to be, what would our px and py be here? Well, px would end up being minus p sine 55 degrees, right? And why is this? Well, it's sine 55 degrees because we can see that it's the opposite side to our angle that we want here, and it's negative because it's pointing in the negative negative x direction here, right? So we want to end up with a negative quantity for our I hat, right? And if we want p to be a unit vector, if we really want this to be p hat, then the magnitude of our p here, this would really be the magnitude of p hat, is just going to be 1, right? So if we do that calculation, we're going to end up finding that this is minus 0.82. And if we wanted to take a look at py in much a similar way, we would end up with a minus magnitude of p hat cos 55 degrees, and this is going to give us a, this is going to give us a minus 0.57, okay? And so what have we really done here? Well, we've calculated the two quantities that we need to build our p hat vector, right? So p hat is really going to be minus 0.82 I hat minus 0.57 j hat, okay? And this is the unit vector pointing in the direction of our vector p. Okay, so now we have unit vector and magnitude, and we know that p is going to be equal to p pointing in the p hat direction. So we could take this magnitude that we have calculated here, which I'll box off, and our direction, and this would give us a really nice way to sort of write out the vector components and then the magnitude, so our p hat and our p, and give us our full p vector in terms of, well, written as a true vector, right? So that's how we find p. I mean, either way. So if you guys were doing this problem for an assignment, I mean, either one of these solutions, if you just wrote down points 145 degrees clockwise from E, that would be fine. But if you need to do a more complicated calculation, like I'm going to sort of demonstrate in the next two parts of the problem, it might be useful or even required for you to be able to calculate the actual vector direction here. So to calculate p hat, to be able to use it to do a calculation, okay? And we'll take a look at that here in part C. So in part C, what are we doing? We want to find tau. Okay, so we want to find the torque acting on our dipole here. So again, I'm going to do this in both ways. We found the scalar p. We found the magnitude of our dipole moment, and so we can use Pe sine phi. We have phi. We know E. We're given E in the problem. We just calculated P, so we could easily do this calculation. We would find that this is 2.0 times 10 to the minus 29. That's our P that we just calculated. We know the electric field because it's given to us. We know what phi is. That's 145 degrees. And if we did that calculation, we would find 5.7 times 10 to the minus 24 Newton meters. Okay? And again, we could, in this case, again use the right-hand rule. Back to our drawing here, we could use the right-hand rule to make our index finger point in the direction of P, our middle finger point in the direction of E. That's a little bit of a stretch here, but our thumb would then point out of the page, point towards us out of the PDF, and it would show us that our tau is pointing up and out of the page, right? And so that would kind of give us, I mean, you could write something like right-hand rule implies tau points out of the page, okay? But we could also treat this like a full-blown vector problem. We could also use, so I'll say or, we could use tau equals P cross E, right? So then we have our P, and I'll rewrite it here. We have our P, this is equal to 2.0 times 10 to the minus 29, and we have our P hat. So this is the P magnitude, and the P hat gives us our direction, 0.82 I hat minus 0.57 j hat. Both of these are negative, right? And our E, if we wrote it down as a vector, we would end up with 5.0 times 10 to the 5 in the I hat direction, right? So if we look at our drawing, E points only in the I hat direction. Okay? Right. And so now what we need to do is just simply take this cross product. And I kind of wanted to do it this way because I wanted to demonstrate a cross product for anybody who is a little bit rusty with it. And I have a certain way of doing cross products. There's a few ways to sort of remember how to sort of do the cross product. I'll show you the way I do it. You don't have to do it this way. You can use any way that you've been taught. Some people just sort of memorize the sequence of inputs that you need to pull out your I hats, j hats, and k hats, but I do it this way. So I'll show you guys how I do it. I would say something like this, and then I would just write this down as well. We can see that this is going to be P, the magnitude, times E, the magnitude, times the cross product of P hat, I hat, right? And so this is just going to be, I guess I'll write it out here again. This is going to be 2.0 times 10 to the minus 29 times 5.0 times 10 to the 5. And then we're going to want to do this cross product here. So the way I do the cross product is I will do I hat, j hat, k hat. It's kind of like this writing of this determinant. And then I'll just put in the values. So these are this next column here is going to be my p hat unit vector, right? So this is going to be minus 0.82. This will be minus 0.57. And this one will be 0. And I didn't maybe leave myself enough space here. This will be j hat, k hat, okay? And so this is the I hat, j hat, and k hat components of my p hat. And then the direction of our vector E only points in the I hat direction, so it's only a 1 here with zeros here, right? And so at this point, I just do this determinant. You can do whatever you would like to sort of remember how to do your cross product, okay? And so what does this tell me? Well, this tells me that, so again, I still have these prefactors out here. So I have 2.0 times 10 to the minus 29, 5.0 times 10 to the 5, and then I have, so I'm doing the sort of determinant in my head here, right? So to find the I hat contribution, I have this times this minus this times this. And if this is not the way you do the cross product, that's fine. Do it however you normally do it. Or if you're curious and don't know how to do it this way, ask me. I'll be happy to go into it. I find this is a nice way to remember it without having to sort of memorize a bunch of complicated sort of equations, right? And so this is going to end up being 0 I hat. Now for j hat, I just exclude this column, and it'll be this times this minus this times this. Again, it'll be 0 j hat. It picks up a pre-minus sign. And in this case, over here, we exclude k hat, and we look at this times this minus this times this. So this is the only term that actually contributes, but it'll be minus this times this, so it'll be 2 minus signs. So we're going to pick up a 0.57. Oops, that should be a k hat. Okay, and so there's only a contribution in the k hat direction, and we have this value additionally, right? So if I take this and multiply it into this and this, we're going to end up with a 5.7 times 10 to the minus 24 k hat, because it's only k hat that it's pointing in that direction, Newton meters, and this is our tau vector. Okay, and that's again the same value that we found over here, and k hat is this pointing out of the page thing, right? So if we have a right-handed coordinate system, I hat cross j hat equals k hat, and if you use the right-hand rule on this, we have a right-handed coordinate system, and our k hat points out of the page. This little circle with a dot in the middle of it is kind of what I'm going to use to indicate a vector pointing towards us, pointing out of the page, right? So this is like sort of like a dart heading towards us, right? And if it was heading into the page, I would use the symbol this. This would be like the dart going away from us, right? Like the flights or the feathers of the dart going away from us. So this would indicate pointing into the page. But in this case, our k hat points out of the page. We have a right-handed coordinate system, and we have our answer here in vector form, okay? Finally, we are looking at part D here. And in part D, we want to find the potential energy. So we want to find U. Again, we can do this pretty simply because we have the scalar quantities that we need. So U is just equal to minus PE cos phi. And right away we can just sub in numbers. This is going to be minus 2.0 times 10 to the minus 29. That's our P. Then our E has a magnitude 5.0 times 10 to the 5. And cos 145 degrees, right? And if we do that calculation, we find this is 8.2 times 10 to the minus 24 joules, okay? We could also do this in its vector form. And so I'm not suggesting that the vector form is always better, but we want to be able to do that in case we're given a problem that's a little bit messy and we can't very easily do it sort of purely as scalars, right? There may be situations where these vectors are all slightly twisted, and we need to find the sort of vector results for it, and then do this as a full vector problem. So we should be able to do that. And so if we wanted to, we could do this like this. We could say minus p the vector dotted into E. And so this is just going to end up being, so we write down our p, but our negative p now. This should be a vector that almost looks like a hat. And so what do we have? We have minus 2.0 times 10 to the minus 29. This is pointing in the direction minus 0.82 I hat, minus 0.57 j hat. And this is dotted into 5.0 times 10 to the 5 I hat, right? And again, we want to remember how to do these dot products. The I components will multiply. There is no other j component, so this j part will not contribute. And so what do we end up getting? We end up getting, well, there's two minus signs here, right? So we're going to have this minus that was a leading minus sign. We also have this factor from in here, so minus 0.82. And this is going to multiply 2.0 times 10 to the minus 29. And 5.0 times 10 to the 5, right? And so this is going to give us a scalar result, right? This is the scalar product, our dot product, so it's going to result in a scalar. And if we do that multiplication, we're going to end up finding that this gives us 8.2 times 10 to the minus 24 joules, again, as it must, right? In both cases. Okay, so that would be the solution to this problem. We're now going to move on and take a look at the electric field outside of a dipole. We already did this three videos ago maybe, but we're going to take another look at it and sort of generate a more general, like in the previous video we did it sort of numerically. We looked at the actual value of E given two different Q values, right? But we're going to look at it more like an equation here. We're not going to be given values, and we want to generate an expression, a general expression that we could use for this value. Before I get into it, though, let me pause one more time and save, and we'll get back to it. Okay. All right, so now on to the problem. So this is directly from the textbook again. This is example 21.14. An electric dipole is centered at the origin, so we have our dipole down here. This is our origin here. And excuse me, is centered at the origin, and it is sort of laying in the positive. Well, its P is pointing in the positive y direction, right? We can see it here. We want to calculate the approximate electric field at the point P up here, and we're going to see that we need to kind of make an approximation to be able to write this down concisely. And so I guess let's just get down to it, right? So we're going to find that to be able to write this expression, we are going to need to use this binomial expansion. We're going to kind of see how that works and why that would be in a second here. Okay, so what does our solution look like? Well, let's start off. So we know that for a point charge, and basically this is just 2 point charges, right? So for a point charge, we know that we can write our electric field, the magnitude of our electric field, as k q over x squared, right? Or in this case, I guess since we're dealing in the y direction, this would be y squared, right? Or if we wanted to, we could change our k into 1 over 4 pi epsilon naught, okay? Again, q y squared. So really, what do we have here? We just really have two point charges. So if we wanted to, we could write this down as EY, and maybe I'll make a note right here. We can see that the electric field on this line on the y-axis, because our dipole is lined up with the y-axis, the electric field has to only operate in the j hat direction, only up and down, right? If we were dealing with a point not on that axis, things would get much more complicated, and we couldn't just look at EY here, at our contribution in the y direction. We would have to look at the sort of full-blown vector problem, and things would get much more complicated. But for this example, we're only interested in looking at the electric field right on x equals 0, right on the y-axis. So let's do that here. So on the y-axis, we can see that, what are we going to have? Well, we're going to have q over 4 pi epsilon naught. This is our k, right? And then we have 2 point charges, right? So I've just factored this out. Basically, we're looking at 2 point charges. Our first point charge, let's look at our positive charge, right? So our positive charge is going to go like 1 over y squared, right? Because we factored out the q here. So it'll go like 1 over y squared, but what's our y here? Well, our y is really our distance from our field point to the center of the dipole, but our positive charge is a little bit closer to us, right? So it's going to be, so our y is really going to be replaced with y minus d over 2, right? Since this is d, we're taking away d over 2, right? So what do we end up with? We end up with 1 over y minus d over 2 squared, right? And this is just this y that would normally be used for our point charge, but it's a little bit closer than what we call y in this diagram, right? And then for the negative charge, well, we pick up a negative sign. I mean, I can probably write it like this. So we'll add in the contribution from the negative charge now. That's going to be, our q is negative here, right? So a negative 1, right? Because we factored out the q. And I'm a little worried that I'm making this more complicated than it needs to be for you guys. Let me actually write this one time before I kind of write it in this form, and then it'll be maybe easier to see, right? So let's look at the contribution only from this positive charge, right? So if we look at only the contribution from that positive charge, it'll look like this: 4 pi epsilon naught, and then we're going to have 1 over, and what did I say? I said y minus d over 2 squared, right? So that's the contribution only from the positive charge. It's basically just the contribution from a single point charge. Then we need to add another contribution from the negative charge, but this one's going to come in with a minus sign, right? Because it's a negative charge, and this one's going to be y plus d over 2, right? Because we have this additional space of d over 2. So now that we've written that down, I'm going to factor it out the way I was trying to write it before, that I thought might have been skipping too many steps. Okay, and so factoring out this q over 4 pi epsilon naught, now we can see that we have, and I'm just going to move this minus sign down, we're going to end up with this expression here, okay? And so this is like our kq. This is our contribution from the positive charge, and this is our contribution from the negative charge, okay? So let's work with that a little bit. We can see that this is going to tell us that EY is equal to, and so what I'm going to do here is I'm trying to manipulate this into a form where I can apply this binomial expansion, the binomial expansion that you see here. Okay, so let's start working with it. So I can factor out a y from the basement here. I'm going to do it in 2 steps. So let's say we do this, okay, and then I'm going to have 1 over, let's say I factor out a y, so I'm going to have 1 minus d over 2y, and the whole thing is squared, right? And same thing on this one, factor out a y, 1 plus d over 2y, whole thing squared. Okay, and now I'm going to pull the y out of the square here in the basement, and that means I can rewrite this as q over 4 pi epsilon naught 1 over y squared 1 over 1 minus d over 2y squared minus 1 over 1 minus d, and there should be a plus, 2y squared. Okay? And because the binomial expansion makes use of things written in this form, I want my power to be not in the basement here. I want it to come up, and so let's rewrite this one more time. Q over 4 pi epsilon naught y squared, and this will be 1 minus d over 2y to the minus 2 minus 1 minus d, that should be plus again, sorry, 2y to the minus 2. Okay, and now we can see that because we're looking at so for y much greater than d, which is the idea here, we want this point to be fairly far away from our dipole, so our total y here is going to be much larger than d. And in that case, for y much larger than d, we can see that this is telling us that d over 2y, or the absolute value of d over 2y, is much less than 1. Okay? So once you've convinced yourself that that's the case, then we can use this binomial expansion again that we see up here, and we can rewrite our terms in these braces inside here, right? So we can see that 1 minus d over 2y to the minus 2, well, that's going to go like 1 plus minus 2 times minus d over 2y, right? And so I can just rewrite that as 1 plus d over y. And our right-hand term, our 1 plus d over 2y to the minus 2, will be approximately equal to 1 plus minus 2 times d over 2y, right? No minus sign here because it's positive here, right? And so again, I can rewrite this as this, what we see here. And so substituting these two results back into the result that we have here, this is telling us that our electric field at the point P is only going to point in the y direction, and it's going to have a magnitude q 4 pi epsilon naught y squared 1 plus d over y minus 1 minus d over y. Okay, and if we clean this up, we can see that these ones are going to cancel. We're going to get 2 copies of d over y, and so we end up with this expression here. Oops. And I can clean that up a little bit. Let's write that like this. And one more simplification that we can make here, we know that QD, well, that's what we call P. That's the magnitude of our dipole moment, right? And so one final simplification, EY is equal to P over 2 pi epsilon naught y cubed, okay? And this is an interesting result. Why? Because we can see that the electric field, along this line at least, is going to go like the distance cubed, right? So we see here that we have y cubed. Now let's think back. For a point charge, how did our electric field go? Well, we wrote it down right here. This is for a point charge. Our electric field goes like 1 over the distance squared. For a dipole, it goes like 1 over the distance cubed. And we probably don't remember right now, but if we think about it, for an infinite wire, so this is like an infinite, like an infinitely long charged wire, let's say, or a charged line segment. We found that E was equal to our charge density over 2 pi epsilon naught r. So in this case, it went like 1 over r. So for an infinite wire, 1 over r. For a point charge, 1 over r squared. For a dipole, 1 over r cubed. For the infinite plane, we found that E had no R dependence. E went like again, our charge density over 2 epsilon naught. So for the plane, it goes like 1. It doesn't have any distance dependence, right? And finally, we haven't done this calculation, but if we did it for a quadrupole basically being like 2 dipoles sort of jammed together, we would end up finding that for a quadrupole, and how do you spell that? I think it's like this. For a quadrupole, which we haven't done the calculation for, but we would find that E went like 1 over r to the 4, right? So depending on the charge configuration and the system that we're looking at, this is kind of a nice way to think about it, right? We have an infinite plane, it goes like 1. We have an infinite wire, the electric field outside of that goes like 1 over r. Then for a point charge, it's 1 over r squared. Then for a dipole, it's 1 over r cubed. And for a quadrupole, it would be 1 over r to the 4th. Okay? And so that's basically it for this video and for this chapter. I will see you guys in the next one.